This I have proved earlier. So I'll skip this. Let me take an example. A is this upper triangular matrix 1, 2, and 1, 3. Let's find the eigenvalues of A. So to find eigenvalues of A, I look at the characteristic polynomial which is determinant of x times identity matrix minus A. So this is determinant of x minus 1 minus 2, 0x minus 3. This is this quadratic equation. So eigenvalues are x equal to 1 and x equal to 1 and x equal to 3. These are the two eigenvalues. They are in my field of real numbers, and therefore we will have eigenvectors. Eigenvectors are going to be linearly independent because eigenvalues are distinct. If eigenvalues are distinct, then eigenvectors will be linearly independent, and this A is a 2 by 2 matrix, and therefore it is going to be similar to a diagonal matrix. So this matrix is diagonalizable because there is a basis of eigenvectors, and these eigenvectors are linearly independent because they correspond to distinct eigenvalues. Let's calculate the eigenspaces. There are two eigenspaces, V1 and V3, corresponding to eigenvalue 1 and 3. So how to find V1? It is set of all vectors V, so that A minus I times V is 0. V3 is the eigenspace corresponding to eigenvalue lambda. This is all vectors, so that A minus 3 IV equal to 0. This is a system of linear equations, homogeneous system of linear equations. This is another homogeneous system of linear equations. So we solve these systems of linear equations. A minus I times V equal to 0. Find all V so that A minus I V equal to 0. A minus I is this matrix. This matrix has rank 1 because there is only one non-zero column vector. So this is rank 1. So null space is one dimensional, but this V1 is the null space of A minus I. So this is one dimensional. Okay, and V3 is also going to be therefore one dimensional because there is nothing common between V1 and V3 except the zero vector. So A minus I is equal to this, and so you can solve for the eigenvectors by solving Ax equal to lambda x. Lambda was equal to xy, this is equal to 2x, 2y, this is 0, this is 0. Just a minute. 2y and 2x, and that is, yeah, we have to solve this system. So y equal to 0, right? Y equal to 0. Once y equal to 0, then my eigenvector is x0 because there is no condition on x. So therefore the eigenspace is linear span of 1, 0. And similarly, look at eigenvalue 3. Then you form this matrix A minus 3i. This is again rank 1 matrix. So null space will be one dimensional, and therefore eigenspace corresponding to eigenvalue 3 will also be one dimensional. You solve this system A minus 3 I V equal to 0, and again you will get that V3 is linear span of 1, 1. So there are two eigenspaces. One is in the direction of 1, 1, and another is in the direction of 1, 0. These are the two eigenspaces, and the only vector which is common between these two eigenspaces is the zero vector. Okay, and the sum of the dimension of these two eigenspaces is 2, which is the dimension of the whole space in which the eigenspaces are living. And the matrix is diagonalizable because the two eigenvalues are distinct. Corresponding eigenvectors will be linearly independent. These two vectors are linearly independent. They constitute a basis of R2 on which my matrix is acting, and therefore this matrix is diagonalizable. Let me give you an example of a matrix which is not diagonalizable. Okay, so let us use this notation I for the complex number root of -1, and look at this matrix: cos theta sin theta, first column vector, second column vector minus sin theta cos theta. This is the matrix of rotation. Yeah, if this matrix is acting on first basis vector, I get the column vector cos theta and sin theta. So E1 under the action of A is mapped to this vector whose coordinates are cos theta, sin theta. Okay, this is my AE1. E1 maps to AE1. So E1 is not an eigenvector because E1 is not being mapped in the direction of E1. Okay, so E1 is not an eigenvector. AE2. What is AE2? AE2 is the second column vector of the matrix, and that is the perpendicular vector. This is the perpendicular vector. This is 90 degrees. This is AE2. So AE2 is also not equal to some lambda times E2, where lambda is a real number. So I think of this as a real matrix. Then eigenvalues have to be real, but in order for them to be eigenvalues, but they are not real. You see the characteristic polynomial. Characteristic polynomial of this matrix, determinant of xi minus a, is determinant of this matrix, and you write down the determinant. It is x squared minus 2 cos theta x plus 1, and this factors as x minus e to the I theta and x minus e to minus I theta. So if you think of A as a complex matrix, A is a 2 by 2 complex matrix, then e to the power I theta and e to the power minus I theta, these are the eigenvalues. If you think of A as a real matrix, okay, real 2 by 2 matrix, there are no eigenvalues, because the roots of the characteristic polynomial are complex numbers. Okay, if theta is not 0 or 2 pi, then the roots of the characteristic polynomial are not real, and therefore this matrix A has no eigenvalue, real eigenvalue. The two eigenvalues are e to the power I theta, e to the power minus I theta. Okay, so this real matrix has no eigenvalues, because how can it have eigenvalues and eigenvectors? Because what it is doing, it is rotating vectors by theta. So no line is mapped to itself. Each line is being rotated by theta. So the direction of the original line is changing. Yeah? The image of a line is mapped to another line, is a line, and the angle between these two lines is theta. So there is no one-dimensional space. This is mapped to itself. Eigenspaces. If I have an eigenvector v, then AV equal to lambda v. So the one-dimensional space, which is linear span of v, is mapped to itself. But there is no line which is mapped to itself under the action of rotation by theta, where theta is not 0 or 2 pi. Okay? So this real matrix, which is the matrix of rotation by angle theta of R2 in anticlockwise direction, it has no real eigenvalue. Okay? Yeah? But the complex eigenvalues are e to the power I theta, e to the power minus I. And they are distinct. E to the power I theta, e to the power minus I theta. If this is my complex number, this is the conjugate of the complex number. And I'm here assuming that theta is not 0 or 2 pi. Then z and z bar are distinct, and distinct eigenvalues have distinct linearly independent eigenvectors. You can go back and solve your system of homogeneous equations and check that the eigenvector corresponding to this eigenvalue e to the power I theta is 1 minus I transpose. This is the column vector 1 minus I. Okay, you have to solve the system, homogeneous system of two equations in two unknowns to find eigenvectors, and the corresponding to for minus I theta, the eigenvector is minus I1. Now notice that these two eigenvalues, they are distinct, but the eigenvectors are perpendicular. These two eigenvectors are perpendicular. Okay, yeah. Okay. Now, there are many applications of eigenvalues and eigenvectors. Let me show you one application. At many times, we are faced with the problem of finding powers of a given matrix. Let us say I want to find 8th power of this matrix. Okay, 8th power of this matrix. Yeah, of course, you can multiply by brute force and get hold of the 8th power. Let me show you, using eigenvalues, finding powers of matrix is an easy problem. Yeah. So first find the eigenvalues of this matrix. They happen to be 2 and 1. So take the corresponding characteristic polynomial. This is the determinant. This is the determinant of x minus 4, 3, minus 2, x plus 1. Okay. So when I put x equal to 2 and x equal to 1, this becomes 0. So 2 and 1 are eigenvalues of this matrix. And so these are two distinct eigenvalues. And so corresponding eigenvectors are going to be linearly independent. So this matrix is diagonalizable at once. Yeah, diagonalizable matrices are those who have a basis of eigenvectors of the whole space. But this matrix is acting on R2. There are two real eigenvalues, these are distinct, so corresponding eigenvectors are linearly independent, and therefore there is a basis of R2 of eigenvectors. So this is a diagonalizable matrix, and eigenvalues are 2 and 1. That means that if I make the matrix P whose column vectors are eigenvectors 1 1, yeah, then this times AP, this is P, is diagonal matrix. So 3 2 is the eigenvector corresponding to eigenvalue 2, and 1 1 is the eigenvector corresponding to eigenvalue 1. So this is the equation. Yeah. So I get that P inverse AP is this diagonal matrix. Yeah. So the column vectors are the eigenvectors, and D is this diagonal matrix. So, and P inverse, you can find out P inverse. You can find out P inverse very easily. That happens to be this, and therefore P inverse AP is diagonal matrix D, and therefore A equal to P times D times P inverse. So I have factorized the given matrix as a product of three matrices: a invertible matrix whose column vectors are eigenvectors, diagonal matrix, and the inverse of P. Now finding powers is an easy matter. Let us find out A8. A8 is this. A8 is because A is equal to PDP inverse. So this is the 8th power. And now we juxtapose these 8 powers. Yeah. So this P inverse will get cancelled from the next P, etc. So I just get P D8 P inverse. Finding 8th power of a diagonal matrix is an easy problem. Just take the 8th power of diagonal entries and now multiply, and I get this. Okay. So computing powers of a matrix, once I have eigenvalues and distinct linearly independent eigenvectors, that is, the matrix is diagonalizable, then the powers of a matrix can be computed very easily. If first I calculate the eigenvalues and then write the equation, similarity equation, P inverse AP is equal to diagonal matrix. Using that similarity equation, you can find out all the powers of